we're going to get started again. And this is Ayush with DKIM and Email Wallet.
Sweet. Yeah, so there's a bunch of people who have been working on this stuff. Me and Sora and some Preeti did a lot of the early work, and now we have a bunch of other support from Xerox PARC and PSC to continue doing things like Email Wallet. Okay, so what is the high-level problem that we're trying to solve here? Is that same with all the other identity things, we're trying to get off-chain data on-chain in some verifiable manner. Unfortunately, most ZK attestations require on some centralized attester making some signature. MPCs work and enclaves work, and a lot of people even have centralized proxies or centralized attesters. But ultimately, you're trusting some other party to create a signature, often to verify that on-chain. And I think it's really difficult to necessarily justify this with the fact that you want this to be as decentralized as possible. So one idea around this is that you can kind of get data, instead of being attested, to be provenant, meaning that you can verify the data directly from the Web2 service by kind of hijacking an existing signature that they have, and you can prove and extract arbitrary information about it, which makes that provenant data programmable. And so one specific signature that we found that allows you to get this provenant data is signatures on your email. So it turns out every single email you've sent or received since 2017 has an RSA signature of the SHA-256, of the from field, the to field, the subject, the hash of the body, another SHA-256 hash, with a key. This public key is posted on DNS. So for gmail.com, it's on like google.domainkey.gmail.com. And if you have some bespoke mail server, it'll probably be some other random string. But basically, you can access this key on DNS. And every mail server holds the private key for that public key. And so what happens is with ZK email, you can verify this DKIM signature inside a ZK proof, and subsequently say, I only want to reveal specific parts of this data. And so specifically, when you send the email, your email domain server will construct an RSA signature and attach it to the email. When the email is received by someone, they'll make the ZK email proof and then send that on-chain. That proof will only reveal specific public fields. And so, okay, like in practice, what does this look like for, like, let's say you want to verify your Twitter username on-chain? Well, ideally, you verify Twitter's signature, which is exactly what we're going to do here. So for instance, what you can do is you can say, OK, I want to get like this username that Twitter is like stuck at the bottom of this email on-chain. And so to get that, first you're going to verify, like in the headers, if you hit like view more, there's like a DKIM signature and a SHA hash, and we're going to verify that against the like from, the to, the subject. You hash the body. It turns out you can actually hash, because you're proving knowledge of pre-image, you don't have to hash the entire thing. You can start in the middle and then hash all the way there to the end. And this proves knowledge of a pre-image and allows you to only parse a much smaller subset than the entire email. And so for HTML-heavy emails like this, what would normally cost 10 million constraints only costs 1 million constraints if you can cut it down to just this section. Then we have a ZK RegEx circuit that allows you to run RegEx on this information and extract out some string. And so in this case, what we're going to be looking for is some string of characters longer than the max Twitter username, so it can't be injected. And then subsequently, you can make mask specific parts and make that public or private. Sweet. And so there's a bunch of cool stuff you can build with this. You might have seen like ZK P2P, which does, if you can verify emails, then you can verify, for instance, a Venmo email you received, prove that email on-chain, and then unlock money the other way. And so you get these kind of like sort of weird permissionless like bridges between off-chain and on-chain information. And this is actually pretty sweet. I think it's actually live on mainnet now, so we can change that link. Twitter, so if you go to like twitter.prove.email, you can do that exact demo that I showed in the browser. We had various collaborators build other things. Someone built a proof in GitHub, in which case you can basically prove you committed to some GitHub repo, which is nice for like donations. Prove you own you belong to some organization. So it turns out you can adapt this like RSA SHA-256 circuit. It's a very generic tool, and you can use it to do things like JWTs as well. And so this allows you to take some like sign in with Google or sign in with Facebook or whatever, and you can extract out, for instance, just the email domain or the fact that you log in as some email address or something like that. Another cool thing is you can like reuse KYCs in different places. So if you already did a KYC with Coinbase, and they sent you a confirmation email saying, we've confirmed your KYC, you can now reuse that KYC on some other service and have the anonymity set of, say, everyone in Coinbase, so that only Coinbase can de-anonymize you. And then I guess one that we've been working on for the last couple of months is like Email Wallet, which you can imagine being like an account abstraction wallet that uses this primitive. And so the idea here was that self-custody wallets are the best of all the worlds, but often onboarding people requires like an intuitive early experience in which you're not memorizing a seed phrase. And so one idea for this is you basically punt the verification of your account abstraction wallet to your email provider. And so what you can do now is you can say, for instance, if I assign some account abstraction wallet on chain to a specific email address, I can set it so that it'll only be authenticated via valid ZK email proofs from that email address. And so this is cool because, yeah, there's now this additional signature being generated by your mail server that you don't own, but it means that the onboarding can just be sending someone an email. And there's another cool thing that we have, which is that it doesn't need to just be sends. You can actually call like arbitrary on-chain functions with this wallet. And so we have this like extension framework that lets you write a 10-line Solidity contract and say, this is how I want the call data to be interpreted on-chain. And subsequently, you can send any data in an email and call any contract you want. So we have a testnet demo here. It should be mainnet by like today and tomorrow. We just had it audited. And the idea is you select like the amount of tokens you want to send, your target email, you hit send via Gmail, and it'll format an email in Gmail with this like to or CC and like some subject that will then be like regex parsed inside the ZK circuit. This on-chain, you'll imagine you'll get a ZK proof, as well as, for instance, the to being parsed out, the like token name being parsed out, and the like masked email address being parsed out, and subsequently that can trigger the transaction. And so you can imagine what this looks like is like for this sending email, it'll deploy this specific wallet, and then do like the actual Etherscan transaction. And so one interesting thing is to consider like what exactly are the trust assumptions of different parties in this like whole flow. And so first, when like user 1 sends an email to user 2, they're going to CC some relayer. This relayer is going to make the proving way easier to do. You can actually ignore this relayer and just create the proof yourself and send it on chain yourself, but this requires you to like do an extra step. And so we found that CCing the relayer is more intuitive, and if this step can be decentralized and self-hosted, then we think that's OK. Great. This relayer can now actually keep the privacy of both email addresses on chain. It's kind of not ideal if email addresses are revealed on chain, because then oh, like I can now tie a specific user to some number of assets. And so this gets tricky both with now Gmail having like financial information about you, and also just people probably don't want their transactions on chain linked to their real name / identity. And so the relayer is going to salt these email addresses and then put them as public outputs of the proof. It's going to get sent to the AA smart contracts. These are going to verify the proof, and so it's going to, that token and the number that we extracted is going to map it to the actual token. It's going to verify the proof, and it's going to look up the mail server key. So remember, that public key that we're actually verifying with is on DNS, and so that needs to be mirrored in some on-chain contract. Subsequently, it authenticates user 1's account, can now control the amount of money specified in the proof, validates that user 2 can actually access that like private salt that we assigned to them, and subsequently creates an account for them, and then can transfer the money. Sweet. So what are like some of the additional layers of complexity you can add on top of this is you basically want that relayer to be as decentralized as possible, because that thing is actually making the proof. It doesn't have the ability to steal your funds because it's verifying Gmail signature, not its own. But it does have the ability to like censor you. It can just say, I don't want to make a proof for you. And so if you have a decentralized relayer system, imagine you have like 10 relayers. They can all basically like, you can trigger any one of them. And imagine only one of them holds your like salted randomness. And like, how can one relayer get that randomness from another relayer if that relayer is attempting to censor you? And so you can actually use like a PSI, like private set intersection protocol, in which like these relayers have like committed to like say like, okay, I'm like handling these wallets on chain. And subsequently, you can now say, okay, like I have a transaction for this wallet. I want to look this up in your database. And because the lookup is actually private, they don't know which value you're looking up in their database of salt. They can't censor you without censoring everyone. And so that's quite interesting. And I think this is like broadly having PSI in a ZK circuit is like a pretty cool new primitive that I think can be used for a lot of interesting stuff. And then extension, so this currently like the demo you saw was just sends, but you can also trigger swaps and whatever else. And a developer only knows Solidity can define a new thing. So the DKIM keys. So basically one interesting thing you can do is these DKIM keys rotate every 6 months or so. And so one problem with this is that you now need some parties, and sometimes these keys get leaked. So what they do is, in order to invalidate all previous emails, a mail server will intentionally leak the private key of their public key in order to say, okay, you can no longer determine if an email before this date was like valid or not. And so normally this would cause a problem, but what we can do is we can actually say, like, if someone sends the private key in plain text on chain, it now invalidates that key. We can do that verification. Another cool thing you can do is to actually mirror it between the two. You can either trust like some network of nodes, like currently we have like a Dfinity system basically in which like there's some other set of like people attesting to this and putting it on chain, or you can actually self-host it yourself. So you can just it's a very simple contract. It just has one function, which is like update the key, and you can just deploy your own contract and point your wallets to your own contract. And we also offer that as functionality in the wallet. And so I think being able to self-host all the things in which there were trust assumptions is like very powerful for people who actually want privacy and care about ownership. Sweet. And then the final thing is, other than the email addresses being unlinked to the balances on chain, you actually also get like UTXO forward compatibility. So with this specific architecture, like each wallet is associated with all the transactions. But if someone, say, wanted to implement this in a way in which each transaction was completely unlinked to every other transaction, it's like basically a UTXO model for each transaction, then you can use like the exact same wallet architecture we have here and like migrate your assets into a UTXO pool. There's like a couple of tricky things you have to take into account for like how you handle the like randomness in like this scenario versus the UTXO scenario, make sure that you're like forward compatible, which is kind of interesting. Right, so I already discussed a little bit of the trust assumptions. One interesting thing is that you're like, when you're receiving some attestation, your personal email account is not like actually attesting that information, it's just receiving it. And so the only person that can fake that information is the one who is signing and sending. Yeah, and I already discussed the relayer can't steal your money, they're just the prover. Sweet, so yeah, we have a bunch of fun SDKs to construct. Like these are all for the Circom circuits, and these have been audited like 1.3 times. And then we have like a set of Halo 2 circuits that do this same thing, but are significantly faster on the client side with a recursive prover. It's all built on Axiom's libraries. And this is like, we're currently starting audit. It should be done like sometime in the next few months. And so this will make client-side proofs. So the idea is that you can use the Circom stuff to make really fast server-side proofs with rapid snark. Should be like, for instance, the email wallet circuits take less than 20 seconds to prove on a server, but they take like a while to prove on the client, maybe on the order of minutes. And so the Halo 2 lets you get like similarly less than 30 seconds proving on the client in your browser, and then recursion punted to a server somewhere else. There's cool tooling to generate like the RegEx circuit, so you can put in a RegEx on what you want to match, and then it'll generate your like circuit for you, both the Circom and the Halo 2 code. Some other cool ideas. So someone like with our SDKs built this like Noses safe that gives you like 2FA for your account. That was pretty sweet. There's a ton of like other like millions of things you can verify. You can verify like any information that's in your email. So like you took a flight, you like live somewhere, you like filed some tax, you got something from Equifax, you like bounty whistleblowing is pretty fun. You can say like, I'm gonna like pay $50 for anyone at like FTX to like publish any email that mentions like this specific person in it. So that's pretty nifty. You can like incentivize people to do that. You can donate to papers because papers usually have their authors' emails in the papers. And yeah, and there's like we have a bunch of other like weird tooling, infra stuff, and like a bunch of other like fun ideas on our GitHub. And then yeah, if people want to like ask questions or check out the presentation or anything, this is like we're happy to answer any questions in the Telegram, support people who want to build apps. People want to build on the core framework. We're also excited to work with you. Yeah, sweet, thanks.
All right, thank you so much, Ayush.
Yeah.
Anyone have any questions for Ayush?
You
Yeah.
mentioned that like DKIM keys are rotated every 6 months, right? So like every time the key is rotated, they release the private key.
So I would say like every mail server we've seen does not release the previous private key, but there is like some set of like best practices, which is like you should consider releasing your old private key. And so in the case that happens, that would like allow people to make fake attestations. So we like that's why this is here, so that you like can't do that in the case that people do decide to adopt this standard. But I actually don't know of anyone that has actually done this in practice, even though it's like a recommended thing to do.
But you you replace the old key with a new key by
Yep.
maybe making sure that the person knows like the old private key, right?
So this is the only way to invalidate a key. So this would like, so the problem is that like if we allowed the like NPC or us or like the signer who's putting this on chain or the self-hosted one to like delete a key, then you could technically like censor transactions. And so the only way to delete a key is by sending the private key, or else you just keep like adding, okay, this was the old key, this is the next key, this is the next key, and like this should all be secure as long as the private key is not leaked. Yep. I think there was a question somewhere here.
Same
Okay. Yep.
Yeah. The relayer.
Yep.
What specifically is the relayer doing in this context?
So what the relayer is doing is because okay, normally when user 1 emails user 2, like user 2 could create this proof and send it on chain. The problem is user 2 is the recipient of the money, like is far less likely to know what like ZK is or that they have to make this proof. And so this would be like 2 extra steps on this user to like click a button somewhere and like upload an email and make a proof and send it on chain. And like it's much easier to just CC a relayer, which then gets the exact same signed email and can just verify that and send it on chain for you.
So it's like a UX.
It's a UX improvement. And if you don't care about relayers, you don't trust relayers, you can also do the entire thing just between the two of you.
Okay.
Yep.
You mentioned that the relayer validates that the user 2 has received the salt. Like what does that mean?
Yeah, so validating they received the salt, we have this like interesting like unclaimed funds model. So the idea is that as long as you send an email to user 2, then you're sure that they have this like private value. And so that's like more or less what it is. There's like a little bit more complexity in how you send to someone that has never made a wallet before, but it's like that's more or less the model. Yep. I think there was some here.
You also mentioned using verifying PSC privates at the
Yeah.
intersection in circuit.
Yeah.
Why that needed for soundness, and was there any like cryptographic challenges to implement that in circuit?
Yeah, okay, so cryptographic challenges for PSI and why do we need it in ZK? So yeah, so PSI is basically like the main difficult thing in here is like hash to curve on like Grumpkin. And so that Geometry already had a hash to curve that we had helped work together on for Plume. And so we could just change that in Circom to do, I think also you have, of course, have the hash to curve. But yeah, this is like the main primitive that allows you to do PSI. Why do you want to do PSI in ZK? So basically you want like, I as a relayer have like committed to some database and I want to prove to you that the value that I'm going to send back to you is in fact the correct value that I've been using for that user on chain with their funds. And so you have to validate that I'm not sending you some random value back. It actually is like a PSI that I ran in my database, but I don't want to reveal to you any of the data in my database. And so the easiest way to validate that you've actually gotten the right value back from their secret database is via a ZK proof of that PSI.
Is that being proved by the relayer once the relayer
Yeah.
owns that?
Precisely, yep. Cool, there was another, yeah.
What's your approach to guarding against replay attacks on the email?
Yeah, so there's a nullifier on the email. I guess I should have mentioned that here, but basically like there's a couple ways to do the nullifier. So our default nullifier right now is just the hash of the RSA signature. So that means that technically your email provider would be able to like hash every email they've ever sent and determine like who is doing transactions on chain. But arguably your email provider can also see that you sent a transaction, which is like send to die to person. So we don't think that meaningfully changes the trust guarantees. But you can also like mask this. So you can say like, for instance, you stick like some specific other private value into that nullifier, and then the information you send on chain is, the information you send in the email is not the like plain text, but some like encrypted / obfuscated value. And then that way, even the email provider involved in the transaction just like sends an email and doesn't know and can't link it on chain. So that's like an interesting direction. We haven't invested in that yet because it's like unclear to us that users or email servers care about this, but it's like, if it turns out to be the case, then that's something that we're interested in doing as well. Yep. Yeah.
Can you talk about how key rotation or DKIM key rotation works?
Yeah, so basically like the mail server that is going to be signing your data, every like say 6 months, they're going to say, okay, like we want to protect against like, our mail server, our data center getting hacked or whatever. And so they're going to say, okay, our like public-private key pair is now going to rotate for every single user sending an email with our service. And in this like one moment, we're going to like remove our old private key and put our new private key, and then on chain, change the DNS record instead of pointing to the old public key to point to the new public key. And so you could actually get this entire process verified on chain if that provider use DNSSEC. And so DNSSEC is basically a chain of signatures on the DNS. And so you wouldn't need any like self-attestation to the DKIM key or trusting any other user to put that on chain. The problem is only like really security-minded websites have DNSSEC on, even though it's like a one-click toggle in both Cloudflare and Google domains. And in the Alexa top 10K domains, there's only about 200 that have DNSSEC on. Luckily, I think like both Proton Mail and Skiff have it on, but Gmail and Outlook like don't. And so for those, you would have to basically like either like punt your DKIM key verification to a contract, say like some multi-sig you trust or like this like Dfinity Oracle we have set up, or self-host it. But yeah, that's basically how like the key actually rotates and how we interact with that key rotation on chain. But I mean, ideally, everyone would use DNSSEC. And so we're hoping that like if this gains more adoption, like people are incentivized to use DNSSEC so that there's actually like more security here. But yeah. Sweet. Any other questions? Yeah.
I missed the beginning of the talk, but
Yeah,
did you cover anything about proof aggregation on the server side?
Proof aggregation on the server. I didn't cover anything, but I can like chat about it briefly. So basically like in the Halo 2 proofs, you can actually imagine that like we are aggregating each proof just as a single proof on the server side because we want to get the like on-chain verifier to be succinct. But you can imagine that, yeah, like if you like waited, say, like 20 seconds and took all of the email proofs in that time and then aggregated them all together, then you would get a succinct proof that can do like 5 transactions at once instead of 1. So like, yeah, aggregation will make the on-chain verification cheaper. So currently we're on an L2, so we like don't really care that much about, it's already like super cheap to do we just don't care about execution gas. But yeah, it would reduce the number of proof signals you have to send in the call data. So aggregation would be useful for like, for instance, a Halo 2 ZKML proof to be more efficient on chain.
How fast is your current aggregation?
So with our most recent version for email wallet, the client-side proof is 30 seconds in the browser, and then the aggregation on a fat server with a GPU and like 128 cores, this is like under a minute to do one proof, aggregated from a prover-optimized circuit to a verifier-optimized verifier.
Cool, thank you.
Yep.
Yeah, so at one point you said that you publicly release your private key to invalidate them. So what exactly is making it public? Like how do you make it public? That's one thing. And second thing is, can latency issues cause like can it help someone to misuse the private key?
Yeah. So this is a great question. So like, what exactly is happening with this private key leaking? So mail servers again, there's a standard which is like, we really recommend that everyone using DKIM should leak their old private keys. But like, people just like don't really do this as far as I can tell. But in the case that they would theoretically post this private key to like their website or something. And then yes, like if the first person to get to that private key, you decided to use it to drain the wallet instead of using it to invalidate the key, then they would technically be able to do that. And so that's why we have like account limits. So like, for instance, like if there is, so the current thing we have is just there's like $100 limit on each account for each transaction, and so the person would have to keep sending transactions. Another way to easily prevent against this is that like each transaction between the time that's actually sent on chain and the money moves, there's like whatever, some like 3-block delay or something. And so now like if someone happens to see that private key, then there is still like some period of time in which like it can be more than 3 blocks, it can be like an hour or something, in which like someone can use that to like invalidate all those transactions. So there's ways around that, but yeah, you're right that there's like this kind of tension between like the incentivization for actually sending this on chain and the incentivization for using that to steal everyone's funds. And so the hope is that I think by adding account limits and adding delays, that you can basically mitigate that almost entirely. Yeah.
Why is it a recommended practice to publish the private key?
Yeah. So I mean, I don't really know if I agree with this, but basically, they say that, for instance, you don't want to be able to prove really old emails because this means that speech that you made a long time ago might be used like against you in like, I don't know, like some future thing in which you like didn't expect it. And so they're saying, oh, like if we release the old private key, then even if you produce an email signature, you wouldn't be able to say that you necessarily said that because you could have faked it with a private key. And so, you know, this is arguable whether it's good or bad. I think it's nice that you can attest to any speech that anyone has made in the past. Maybe someone would disagree with that and would thus want to leak their private key. I think it's telling that I know like no mail servers that have adopted this standard yet. Yeah. And if you know one, please reach out to me. I'd be very curious. I want to see it. Yeah. Sweet.
All right, thanks a lot. Aish.
Awesome. Thank you.